Okay, so here is your unit for how to test review. So we're going to start off, there's a lot of outcomes here. We have to go from 14 all the way through 22. So we'll start here at the beginning. Outcome 14 is all about adding, subtracting, and multiplying. I'll tell you right off the bat, you're not going to have an adding one. It's just too easy. It's combining like terms, and either way, the subtraction one ends up turning into addition anyways, so we don't put an addition one in there. So with subtraction, one thing I told you to do when you're doing subtraction is to make sure that you change the sign to a positive, and then everything else that's in the parentheses are going to change the signs. This becomes negative 5x to the fourth, negative x to the third, negative 2x squared, positive 6x, and positive 12. Once you do that, then it just becomes addition, and you just combine like terms. You want to pay attention to the exponents, as you're going to put this in standard form, it has to go from the highest exponent down. So we have, first of all, the x to the fourth, 3x to the fourth, minus 5x to the fourth is negative 2x to the fourth. Cross those out. Negative, or the next one is going to be your x to the third. There's nothing the x to the third to combine with, so it's just going to be negative x to the third. Then you have x squareds, negative 4x squared, negative 2x squared is negative 6x squared. And 7x and 6x is going to be 13x. And then 10 and 12 is going to be 22. And that will be your final answer, as we cannot combine anything else because nothing else has like terms. Moving on to multiplication, we've got to be careful with the problem like this. It's common for kids to want to distribute this 3 in here, but you can't do that. You have to sort of refrain from doing that because there's rules, and you can't do that when there's more than one term in the parentheses. So what we have to remember is when you have an exponent like x to the second or x to the third, it means that there are that many of them. So x minus 2 to the third means that there actually is 3 x minus 2's. So we write out, x minus 2 3 times. Now, when what I said before is we can't multiply all 3 of them at the same time. You can only multiply 2 at a time. So I told you guys to kind of divide this up here so that you only multiply the first 2. And then once you're done multiplying the first 2, then you can incorporate the third one. For the first one, we're going to multiply here and just go through and multiply everything times everything. X times x is x squared. X times negative 2 is negative 2x. Negative 2 times x is negative 2x. And negative 2 times negative 2 is positive 4. Some quick combining of like terms here is negative 2x and negative 2x is negative 4x plus 4. And then now that we have the first 2 multiplied, we now can incorporate the third one here in the third x minus 2. And now we have to multiply all of those together. So let's use a different color here. So I'm going to do x squared times x, which is x to the third. X squared times negative 2 is negative 2x squared. Then move on to the next one. Negative 4x times x is negative 4x squared. Negative 4x times negative 2 is positive 8x. 4 times x is 4x. And 4 times negative 2 is negative 8. So once we multiply those out, we can then go through and search for any sort of like terms. We have a like term there. We have a like term there. So we'll combine that's actually the same color. So I have x to the third. When you combine the x squared, it's negative 2x squared, negative 4x squared. That's negative 6x squared. And when you combine the x's, 8x and 4x is 12x, and then minus 8. And that is the answer when you are multiplying. Moving on, outcome 15 is all about dividing polynomials, and this is where we introduced synthetic division. So that's the only thing you have to do here is synthetic division. We used to do long division here, but now we just do synthetic division. When you're doing division, you have to ask yourself what makes the divisor 0? What value of x would make this that's called a divisor. The one on the left is called a dividend. The one on the right is called a divisor. So what makes my divisor 0? In this case, if I were to put 3 in for x, then that would make the divisor 0 because 3 minus 3 is 0. So what we do is once we know what makes the divisor 0, we're going to put that number in the corner. And then what you're going to do is then you're going to take the dividend here and write down all the coefficients and constants, being sure not to skip any terms. So if it starts out with x to the third, it should go 3, 2, 1 constant, 3, 2, 1 constant. If any of them are missing, you're going to want to make sure that you place a 0 in the place of that term. So for example, if the x squared was not there, I would have to still put a 0 in its place. I can't just skip over them. This one, though, has all of them. So there's a 1 in front of the x to the third, so 1. Then there's a negative 5 for x squared. And then there's a negative 2 for x. And there's a 24. All we do is write down the numbers, the coefficients, and the constant, no variables. We draw a line a little bit further below just so we can, because we're going to be writing numbers in between there, so we want to leave some space. So that's the setup. What makes the divisor 0, and then our dividend here with all the coefficients and constant. The first step is going to be to bring the first number down below the line. Whatever the first number is, bring it down. And then you start a process of multiplying and adding. You multiply by the box number, the number in the corner. 1 times 3 is 3. And you place it in the next column, and then you add down. Negative 5 plus 3 is negative 2. And then the process repeats. Multiply to the corner number. Negative 2 times 3 is negative 6. And then add straight down. Negative 2 and negative 6 is negative 8. Negative 8 times 3 is negative 24. Now in this case, I ended up with a remainder of 0, which works out awesome. I don't have to put a remainder, but we'll explain what that looks like here in a second. So what ends up happening is you get this answer right here down below. And so what does that mean? Well, you have to look at your degree up here as it's x to the third. Once you perform synthetic division, your answer will always be 1 degree less. Since it was x to the third, it's now going to be x squared. And so we go down the line. 1x squared is just x squared. Then we have our x term, negative 2x, and then our constant. And that's going to be the final answer. Now if, and let me take a step back, if there had been a remainder, let's say a remainder of 10 or something like that, then I would have to add that remainder, which is whatever it is in the numerator, and whatever I was dividing by in the denominator. But since I didn't have a remainder, that is my final answer. The other type of synthetic division you're going to have to do is going to be to evaluate. Now this incorporates a unique rule in math in what's called the remainder theorem. So typically, if you were to be given a function like this, and then I told you that x equals 2, you simply would just substitute 2 in for all the x's, and you certainly can still do that. But what might be easier and quicker is to use synthetic division. Since we know that x equals 2, we can just place 2 in the corner and run it through synthetic division. So whatever x equals, if you're evaluating, just put it in the corner and run it through synthetic division. Be careful not to miss any terms. So we start off with an x to the third, then we have an x squared, then we have an x, but we notice here we are missing the constant. There should always be a constant. So if there is not one, I do have to place a 0 there. Draw a line, just like the previous one, drop the first number down, then multiply. 3 times 2 is 6, add down, negative 2 and 6 is 4, multiply, 4 times 2 is 8, 7 and 8 is 15, 15 times 2 is 30, and 0 and 30 is 30. So what ends up happening here, what's called the remainder theorem, is that when you are evaluating, the remainder theorem rule states that when you are evaluating, whatever you plug in through synthetic division, whatever you get as the remainder is the answer. So the answer to this problem is simply 30. Now, if you were to take 2 and plug it in for x for all these, you would get exactly the same answer. There's just a lot more room for mistakes, though, in evaluating algebraically rather than just using synthetic division. So I recommend using synthetic division if you can. But if you're like, if you don't remember what it is or how to do it, then you can just simply plug it into the x's. Moving on to outcome 16. Outcome 16 is being able to determine whether or not an expression is a factor of a given polynomial. So you have to, and when we talked about this, is you have to remember what are factors. Factors are things that go into a number evenly. So, for example, 4 is a factor of 12 because 4 goes into 12 evenly. So if we're thinking about polynomials, the question is asking, is x minus 6 a factor of that polynomial? Well, you have to ask yourself, if I divide it, then it should go into it evenly. So what we do is we actually just divide this into this. And so we can use synthetic division and use this as my divisor. So what makes my divisor 6 in this case is 6. 6 minus 6 is 0. So that makes my divisor 0, so I can use that in synthetic division. I'm going to run this through synthetic division. So I have 1x to the third, negative 8x squared, 9x, and then 18. If this is a factor, then what I should get is a 0 for my remainder because if it goes into it evenly, I won't have anything left over. So we're looking for a remainder to be 0. So the first number is going to be down. 1 times 6 is 6. Negative 8 and 6 is negative 2. Negative 2 times 6 is negative 12. 9 and negative 12 is negative 3. Negative 3 times 6 is negative 18. And we do, in fact, get a 0 as our remainder. So yes, this is a factor. X minus 6 is a factor of the polynomial x to the third minus 8x squared plus 9x plus 18. We do exactly the same thing in number 5 here. I think did I number these right? I feel like, yes, I did. Just feel like I didn't number them right. So we're going to divide this into the polynomial. What makes my divisor 0 is 2. And I'm going to run it through synthetic division. There's x to the third, negative 7x squared, 4x, and 12. And we're going to run it through. I'm going a little quicker here because we've done synthetic division now 4 times already on this review. 1 times 2 is 2. Negative 7 and 2 is negative 5. Negative 5 times 2 is negative 10. 4 and negative 10 is negative 6. Negative 6 times 2 is negative 12. Yes, this one also is a factor. And that's all you have to do. Okay. You're going to have one that is like this, where you're going to have a graph in which you're going to have to just look at the graph and decide A, B, C, or D, which one is not a factor. So when you look at solutions or x-intercepts, you have to remember that with x-intercepts, it's always going to be the opposite. So if you think about this one here on the far left, x is -2, it stems from that x plus 2 is the factor. Because if you remember how this works with your factors, x plus 2, I would have to set that equal to 0. And when I set that equal to 0, I would subtract the 2 over and get -2. So the factored form is always going to be the opposite sign in parentheses. So this one would be x plus 0.5. This one would be x minus 1. And this one would be x minus 2 in factored form. So we just look at which one doesn't belong. So x plus 2, yes, that's there. X plus 1, ooh, that one's not there. So this is the one that doesn't work. But let's just check and verify. X plus 0.5, yes, that one's there. X minus 2, yep, that one's there. So this is the one that doesn't belong, and so that's the answer. Outcome 17 actually brings us to actually factoring polynomials. So you're going to have two types of factoring in these polynomials. One's going to be a GCF and the other one's going to be grouping. You'll notice the difference right away in that one has 4 terms and one has 3 terms. So when we do this one here, you should be able to recognize like, hey, look, I can take out a GCF. They all have an X. And so we simply just take out an X because that's the GCF. That's what goes into all of them. And then we're going to write what's left over. By taking an X away, this is X squared. This is 4X, and this is -5. Now you're not quite done here because you have to also factor the quadratic. So when factoring quadratics, you have to ask yourself what multiplies to B or C and adds to B or B. So what multiplies to be -5 and adds to be 4? Well, that should be 5 and -1. So when we draw our dead cartoon eyes, X is in parentheses, we will get +5 and -1. Both of those, 5 and times -1 is -5, and 5 plus the -1 is 4. The X also comes down that we factored out initially, and that's our answer. The second one, because there's 4 terms and it's a cubic, you should recognize that that is a grouping type of problem. And we see a grouping later on too when we're solving polynomials. But here we're going to just group in order to factor it. When grouping, you combine the first 2 terms in parentheses, and then you combine the second 2 terms in parentheses. And then you take out a GCF. So I'm going to take out a GCF of the first set, which is going to be x squared. And when you take out x squared, you're left with an x in the first term and just a -2 as the second term. In the second one, you'll see that a 5 is going to be your GCF. So I'm going to take out a 5. When I take out a 5, I'm just left with an x. And then -10 divided by 5 is -2. Now I know that I've done this right because both of my parentheses are exactly the same. The last step in factoring with grouping is to combine both GCFs into one single parenthesis. So the x squared and the +5 will go into one, and the common factor x minus 2 goes in the other. And that is factoring by grouping. Moving on to outcome 18. 18 is all about solving polynomials. So this is the big one. And this is probably where there's going to be the most issues on this test, is solving polynomials. It's a big one, and it can be kind of difficult. So one thing that you will see is the use of your graphing calculator is going to significantly help here. So what we want to do when solving polynomials is to pull up our graphing calculator and use our graphing calculator to see if it will give us one of the solutions. So I'm going to pull up here. Oh, that's not what I wanted to do. Well, we'll just go with it. So first page here, calculator link. And now I'm going to bring back in Notability. And I'm going to look for, in their graphing calculator, one of the solutions. The first thing I want to do is plug it into y equals. So I have 9x to the third, and then minus 27x squared minus 34x minus 8. And so when we get it into our graphing calculator, first thing we're going to do is look at it graphically. Now it does look like I should have 3 solutions, and I do see it crossing the x-axis in 3 different places. So I do know that all of them are going to be real solutions. So to find at least one of the solutions, we go to our table by hitting second in graph. Now from here you can see what you're looking for is where y is 0, and there is only one. So it looks like the calculator is only going to give us one solution, and that is x equals 4, because that's where y is 0. And so what we do is we take that value of 4 and we're going to run it through synthetic division. The purpose of this is to get it into a format that we can actually solve. Right now, we cannot solve it unless we get it into a different form. So by running it through synthetic division, because it's an x to the third, what we end up with is a quadratic, which we can use quadratic formula. So I'm going to plug this in, 9x to the third, negative 27 x squared minus 34x, and then minus 8. So we'll go through here. First number will come down, 9. 9 times 4 is 36. Negative 27 and 36 is 9. 9 times 4 is 36. Negative 34 and 36 is 2. 2 times 4 is 8. And so negative 8 and 8 is 0. A couple things you want to check here. You should get a 0 at the end because you're using an actual solution from the problem. When you run it through synthetic division, you should get a 0 on the end because it's an actual solution. Also, getting a 0 on the end tells you that you did the synthetic division correctly. And so you can start moving forward knowing that this is correct so far. Now, because the problem started out as an x to the third, I know that now I'm going to have an x squared. So the problem will be 9x squared plus 9x plus 2. Ooh, I don't know how that happened. Okay, now that it's a quadratic, we can actually use quadratic formula to solve the problem. Quadratic formula, and I'll change colors here, is x equals the opposite of b, which is now negative 9, plus or minus the square root of b squared. 9 squared is 81, minus 4 times a, which is 9, times c, which is 2, all over 2 times a. 2 times 9 is 18. Sorry. The next step is then to do the discriminant. So 81 minus 4 times 9 times 2, and you're going to do that in your calculator. And so we get x equals negative 9 plus or minus the square root, and I have to do, let's see, 36, that's 7, minus 72 is 9. Oh, that makes it easy. And so, and that's over 18. Now the good news is we know the square root of 9, so we can complete this problem. Negative 9 plus or minus the square root of 9 is 3 over 18. And so we can find our 2 solutions here. Negative 9 plus 3 is negative 6 over 18, which is negative 1/3. And then negative 9 minus 3 is negative 12 over 18, which is negative 2/3. And so there you see I have all three solutions. I should have three solutions. I do. There's 4 up there. Negative 1/3 and negative 2/3 are my other two solutions, giving me a total of 3. Now you can probably guess what's going to happen here because we dealt with imaginary solutions. This is probably going to be one that gives us an imaginary solution. But either way, we're going to plug this into our graphing calculator. Y equals, let's clear that out, x to the 4th minus 3x to the 3rd minus x squared minus 9x minus 12. And so we're going to go ahead and graph this. And so what we see here, and we actually did number 9 for a few of my classes. We already did number 9 as practice. So this, you might already have this in your notes. But when you plug it in there, you're going to see something different. Because the x to the 4th, that tells us we should have 4 solutions. But what you see on the graph is you only see it cross the x-axis in 2 places. What that tells us is that of the 4 solutions, only 2 of them are real. Because there's only 2 crossings of the x-axis, there's only 2 real solutions, which makes the other 2 solutions that we will get, they will be imaginary. So we need to find a solution. So I go to my table. Now it doesn't matter. I can use, in this case, I have 2 of them. I have -1 and I have 4. And you can use either one. It doesn't matter, but you do need to pick one. I tend to pick positive numbers just because they're easier to work with. So I'm going to choose 4. So I'm going to use 4 as my solution of choice, and I'm going to run it through synthetic division. Remember, the goal here is to get it into something we can actually solve. So 1x to the 4th, negative 3x to the 3rd, negative 1x squared, negative 9x, and negative 12. When we do this, the 1 comes down. 1 times 4 is 4. Negative 3 and 4 is 1. 1 times 4 is 4. Negative 1 and 4 is 3. 3 times 4 is 12. Negative 9 and 12 is 3. 3 times 4 is 12. And we do get a 0 at the end, so that's a good sign. Now, because this started out as x to the 4th, I know that my answer will then drop down to an x to the 3rd. Change colors here. So this becomes 1x to the 3rd, or x to the 3rd, plus x squared, 1x squared, plus 3x plus 3. Now, from the previous outcome, looking at this, you should have an idea of how to solve this. Because I have a cubic now with 4 terms, I should look at grouping as a possible solution. I don't have a quadratic, so I can't use quadratic formula, but I do have a cubic with 4 terms, and when we have 4 terms, we can try to use grouping. So let's see if this works out. So I'm going to use grouping. Take out a GCF. In the first one, you get x squared, leaving x plus x squared divided by x squared is 1. In the second one, you get 3 as your GCF, making that x plus 3 divided by 3 is 1. And so it does work, and I know I did that right because the parentheses are the same. And just like in the grouping problems above, the next step is then to take your GCFs, put them in the same parenthesis, and then your common factor, the x plus 1, in the other. Now, unlike the problem above where we were factoring, we're not going to stop here. Because the problem asked us to solve, we actually need to get actual solutions. And to do that, we actually set what's in the parentheses equal to 0. And so what we get is, by the first one, subtracting 3, we get x squared equals negative 3. And then to get rid of the square, we have to square root. Couple things to remember when dealing with square roots. We always have to have plus or minus. And the other thing we have to remember is we can't have negative radicals or negatives in the radical. And so to fix that, we've done this before. To fix this, we place an I out front. And what that does is that makes the radical now positive. Now, the square root of 3 is not a nice number, nor can I simplify it. So this is simply the answer. For the other one, when you subtract the 1 over to the other side, you get x equals -1. And so there's all 4 solutions. You have your 2 real solutions are 4 and -1, which we already knew -1 was the solution. But those are our 2 real solutions. We knew we were going to get 2 imaginary solutions, and they're both right here. Because of the plus or minus, that gives us 2 solutions, plus I radical 3 and then minus I radical 3 is 2 solutions. Moving quickly. Hey, almost done here. Outcome 19 is a new one. Outcome 19, we did not get a chance to do this in the notes. So this is going to be very important because outcome 19 is on your test. And so this is your opportunity to learn outcome 19. Outcome 19 is all about writing polynomials. Now, it's not as difficult as it may seem. You have to remember sort of what we did back up here. Knowing that the solutions here, x equals -2, x equals -0.5, x equals 1, and x equals 2, when we put them in factored form, they go into parentheses and change their signs. And the reason they change their signs is because once you end up solving, you have to move the 2 to the other side and it becomes negative. So if you just remember that the solutions going back into factored form is just in parentheses with the opposite sign, that's really going to help out a lot when you get down here and you're writing a function, because it tells you what the solutions are. It tells you that the solution is 0. It tells you the solution is -3. And it tells you the solution is 4. So what we can do is put those in factored forms in parentheses. Now the first one, 0, there's no real opposite sign there, so you just put x plus 0. But in the other ones, in the -3 in factored form would be x plus 3. And the 4 in factored form would be x minus 4. And we use our previous skill in multiplying to multiply that all out. So what we're going to do is we're going to multiply all this out. Now x plus 0 is simple. I really don't need the plus 0, so it's just going to be x. But I can only multiply 2 at a time, so we do have to separate this. But what makes this easy is there's only one thing to multiply. X times x is x squared. X times 3 is 3x. And that's it. Now I can bring in the x minus 4 and multiply these. X squared times x is x to the third. X squared times -4 is -4x squared. 3x times x is positive 3x squared. And then 3x times -4 is -12x. We can combine like terms here, and so I get x to the third. -4 plus 3 is -1x squared. And then minus 12x. I hope I did the math there quick. I'm just doing this off the top of my head for all these problems. So if anything looks wrong and you don't understand why, let me know. I definitely could have made a mistake myself. And so you get down here and you're like, hey, look at that. I found my function. And it may be your function, but we do have to go through all of the other directions here and make sure that this all works out. Write a polynomial function. Check. In standard form. Check. With a degree of 3. Yep. The highest exponent is 3. Check. Zeros are this. Yep. Well, that's what I used to get this. And it has a leading coefficient of 2. Whoa, wait a minute. I don't have a leading coefficient of 2. What did I do it wrong? No, this is just a really simple fix. If you don't get a leading coefficient of 2 and it's supposed to be 2, all you really have to do is simply just multiply everything by 2. And that'll be 2x to the third minus 2x squared minus 24x. And now we have a polynomial with a leading coefficient of 2. And that's how we write the polynomial. We're going to do this again now with a graph. This is very similar to the problem up above. And so what we have here, since x equals -1, factored form would be x plus 1. Since x equals 2, factored form would be x minus 2. And since x equals 3, factored form would be x minus 3. And so all we do is simply just multiply all those together. X plus 1, x minus 2, and x minus 3. And the same rules apply. I can only multiply 2 at a time. So we multiply this. X times x is x squared. X times negative 2. 1 times x. 1 times negative 2. Okay. Combine like terms. Negative 2x and 1x is x squared minus 1x. I don't really need the 1x. That's going to bother me. And then minus 2. That's a parenthesis. I can finally bring down the x minus 3 and repeat the process. I'm going to write these answers over here. So x squared times x is x to the third. X squared times negative 3, negative 3x squared. Negative x times x is negative x squared. Negative x times negative 3 is positive 3x. Negative 2 times x is negative 2x. And negative 2 times negative 3 is positive 6. I'm going to go over here and combine like terms. So I get x to the third. Negative 3x squared and negative x squared is negative 4x squared. 3x minus 2x is 1x. And then plus 6. Now, a couple things we need to pay attention to here. We want to make sure everything works out. The only other piece of information that it gives us is this y-intercept. It gives us the y-intercept is 6. Now, if you remember anything about anything we've done with either quadratics or polynomials or anything like that, the constant, when an equation is in standard form, the constant always refers to the y-intercept. And so we can go over here, and what we're talking about is this constant right here will always represent the y-intercept. Now, we have a y-intercept of 6. Does it match? Yep, y-intercept is 6. So that is my answer. Done. If you need to have some more practice, I may include some more practice here, at least with big ideas or something like that. Or we can do something if you want to come in during AL. We can do some more practice with this, or we might be able to have time to do a problem before we take the test. Now, on to outcome 20. This is probably the easiest one of the whole test. But basically, this you just have to either look at the equation or put the equation in a graphing calculator and look at it, and basically see how many roots are real and how many are imaginary. Now, there's a typo in this first one here. This is supposed to tell you that this is an x to the fourth, or it's a quartic. So that tells us that we should have 4 solutions. Okay, if we have 4 solutions, how many are real and how many are complex? And this is where you look at the x-intercepts. Anywhere where you see an x-intercept is a real solution. So in this case, I only have 2 real solutions because I only have 2 x-intercepts, 2 real solutions. Now, since I know there are 4 and 2 of them are real, that must mean that the other 2 are complex. Now, this one here, I'm going to have to look at. So I need to go over here and put this in my graphing calculator. 2x to the 5th plus 4x to the 6th minus 5x to the 6th plus x minus 3. And so we're going to look at the graph. And so here we can see that it only crosses the x-axis in 2 places. But because the highest exponent is a 6, I know I have 6 solutions. The fact that I only see it crossing the x-axis twice means that only 2 solutions are real. And that must mean that the other 4 are imaginary. Okay. And 21 and 22, this is the very last problem here. We already did this in a couple of my classes. We already did this problem. So I'm not going to spend too much time with this. But if this is your first time seeing it, then you can go back and or pause it and rewatch it. The goal here is to graph a polynomial. So, and what I told you guys in blocks 5 and 7 is that in order to graph a polynomial, you need a lot of points. Unlike a line, in which I only need 2 points to draw a line, or unlike a quadratic, where all I need is 3 points, a vertex, and 2 random points, with a polynomial, since there's so many more curves to the problem, I need a lot more points. And so what we need to find, these first 3 here are going to get us the graph. I need to find the x-intercepts, and I need to find the local maximum and minimum. So I'm going to show you how we find those pieces using your graphing calculator. So first thing we need to do is plug this into our graphing calculator. So I have 3x to the third and minus 2x squared minus 5x plus 1. And so we're going to use this in our graphing calculator. Now what I'm going to do is I'm going to zoom in. It's a little bit tight in there, so I'm going to zoom in just to make things a little bit easier for me. And so that's much bigger. And so I got a lot more room to work with over here. But what I want to do first is find the x-intercepts. And so finding the x-intercepts isn't any different than when you found the x-intercepts with parabolas, and that's simply just taking second and trace and getting over to the calculate menu, and we look at zeros. X-intercepts are zeros. So we click zeros, and if you remember, we have left boundary and right boundary. So I'm going to go to the first x-intercept over here on the left, and so I just go a little bit left, enter, a little bit right, enter for a right boundary, and then enter a third time for them to calculate it. And so it tells me that the x-intercept is negative 1.1. So I can go over here, write down my first x-intercept is negative 1.1. But I can also go over here and graph it. Negative 1.1 is somewhere right there. Now I can also repeat the process to find the other 2 x-intercepts. So let's go to the one in the middle. So the x-intercept here in the middle is somewhere right here. So I go a little bit left, hit enter, a little bit right, enter, always left and then right. And then enter a third time. And so this tells me that the other another x-intercept is 0.19. So I can go over here to my x-intercepts. 0.19 is another one. I can graph that. 0.19 is probably somewhere right there. And then finally, the third one, 0, enter over here. Again, I go a little bit left, always left first, then a little bit right, enter a third time. And so there's the third one at negative, or not negative, 1 point, looks like 1.6 if I round it. So 1.6 is my third x-intercept. So I go over here, 1.6 is somewhere right in here. Now you can see by getting 3 points, I really have no idea where this graph goes. And this is why we need a little bit more information. So we have this extra piece here called local maximum and local minimum. Basically, all parabolas, or not parabolas, but all polynomials have this little up and down kind of in the middle. And so in the middle of this, you know, when you're looking at a graph that goes like this, every graph is going to have a local area, a local top, and a local bottom, or a local max and a local min. Now it might be shaped the other way. It might be going like this. So you might have, you know, it might have a local min here, then a local max there, but you get the point. And so to find those local max and local min points, we're going to use the vertex, the way to find vertexes or vertices. So we go second and trace, and so here's our minimum and maximum. So I'm going to start off with the maximum first. It doesn't really matter which one you do, but to find the local maximum, I know the local maximum is over here, and so I know it's somewhere up there. So I just got to make sure I'm on the left side, hit enter, and then I'm on the right side and hit enter, and then enter a third time. and it's going to give me a coordinate for that maximum, for that local maximum. So my local maximum as a coordinate looks like negative 0.6 if we round, and then 2.6 is my y value. So when I go over here to plot this, negative 0.6 and 2.6 is somewhere right there. And now I need to find the local minimum. So I go to second trace and then minimum. And so now I'm going to go over here. I know the minimum's somewhere down here. I need to make sure that I'm on the left side first, right side second, and then enter a third time for my local max, or my local minimum, which looks to be 1, -3. So 1, -3 is my local minimum, 1, -3. And so I'm going to plot that, 1, -3. Now I don't need my calculator anymore, so I'm going to get that out of the way so I have more room. But now I have everything I need to graph this. I have where it goes up, where it goes down. Try to draw this as best as possible. Well, it's as good as it's going to get. But there's my graph. That's the graph. And so I have all the points that I need. The only thing that's going to be different now is the addition of what is called intervals, increasing and decreasing intervals, and end behavior. These last pieces here, these are going to be new pieces that we've had that you haven't seen before. Basically, increasing intervals is asking you where is it going up, and decreasing intervals is where is it going down. So where is it increasing? Where is it decreasing? And you can see here it goes increasing again. So we write intervals based on a number system, including numbers, but also infinities. And so we always go from left to right. So when you're doing intervals, you always read from left to right. So because we don't know where this starts, we don't know where this graph starts, we just know that it's got an arrow, so it goes on and on forever in the left direction. I know that the increasing interval is going to start, so we do it in parentheses, it's going to start at negative infinity. Because we don't know where it starts. We have no idea where it starts. I just know it's all the way left here, and I know that it goes on forever. So we know that this is an increasing piece. This is an increasing piece. This is a decreasing piece, and this is an increasing piece. So this increasing piece here starts at I don't know where, somewhere down to a negative infinity. And so where does it stop increasing? Well, it's increasing, and it stops right there at our local maximum. Now, what you need to remember is that when you're doing intervals, we only look at the x values. So we are only looking at these values right here. Okay? And so it goes, increases all the way to this point right here, which is our local maximum. So we go to the local maximum and we look at the x value. So we do this as commas. So this means that it is increasing from negative infinity to 1. Then we have a period of decreasing. The decreasing goes from the local maximum to the local minimum. So we're looking at from here to here. Remember, we only concentrate on the x values. So it's decreasing from negative, let's see, local max. Trying to think of what the heck. So I got that backwards. See, I made it all the way to the last problem before getting that backwards. I put the local maximum and local minimums in the wrong places. Let's see if I can switch these here. You go over here. You go here. Let's bring you back. There we go. See? Look at that. I made it all the way. You guys are probably, the last 5 minutes, you're probably like, what the heck is going on? I got the local minimum and local maximum. I put them in the wrong spots. So the local maximum is actually negative 0.6. So this is negative 0.6 that goes there. And then the decreasing interval starts from that negative 0.6 and goes to the local minimum x value, which is 1. But then we have a period of increasing And so that increasing starts at the local minimum, so right here, and goes to who knows where, but we do know that it goes on forever to positive infinity. So write that here, that it starts at 1 and goes forever in the positive direction to infinity. And that's how we do intervals. The last piece here is end behavior. Basically, how does the graph behave on the ends? Over on this side, it's going down, and on this side, it's going up. But you could have graphs that start like this. So on the left, it's going up, and on the right, it's going down. Or you could have quartics or something like that look like this, and where in which case both sides are going up. So the only thing that you need to understand, this notation is going to be here on the test as well, but as x approaches negative infinity, this symbol or whatever means left, and as x approaches positive infinity, this means right. So when you're asking, does it go up or does it go down, you need to look on the left and then the right. The first one is left, so is it going up on the left side or down? And so what we're looking at here is this piece here. On the left side, it is going in the downward direction. So down is negative infinity. And then on the right-hand side, since the right-hand side is going up, we call that positive infinity. Now, I promised that we would do another one of these before we took the test. And we will do another one of those. We're not going to have time for much anything else. So if you have questions, you need to see me. You can email me or send me a message, or remember that both of you guys have ALs before you take the test. So you could come in, whether you're BD or AC, both of you guys have an AL prior to taking the test. So if you have any questions on anything you saw in this video or while you were doing the review, please come in to AL. That's it.